Okay, welcome to free response problem 2003, Form B. I want my felt tip pen here. I don't like this pen. Yeah, there we go. 2003, Form B. This is an excellent question. If there's one that you really know, it's this problem. I really like this problem. Before we begin, I just want to start by analyzing this problem, and then we'll jump into it. First off, everything counts, therefore it's a gas. Second off, they give us a graph, and one thing I really want you to notice about the graph is we're showing a decrease and then a plateau, and that plateau is going to be really important because that's going to denote equilibrium. That's where the concentration does not change. If you read this graph, it shows you that the concentration of HI is plotted as a function of time, and we know that HI is a reactant. So one thing we want to think about also is this is really a right shift because the concentration of the thing on the left, the reactant, is going down. So it's shifting to the right. Let's go through and solve this problem. I'm just going to do it in order. It says write the equilibrium expression, KC. We're going to write that out, and that's simply going to be the concentration of H2 raised to the first power of the concentration, in this case, of I2 over concentration of HI squared. It's asking us for what is HI at equilibrium. Okay, so immediately, even if it's a really easy thing to look at, I want to go through and set up an ice chart. So always set up your ice chart. Always. H2 gas plus I2 gas. And set up I, C, E, boom, boom. All right, well, we're going to read the question. It says, after a 1 mole sample of HI is placed into an evacuated 1 liter container. Okay, so initially we have a concentration of 1, and that's because it was 1 moles over 1 liter, which ended up being 1. It said it was evacuated. That means this is 0 and this is 0. Okay? That means it must be shifting to the right. Minus 2x, x, x. This is 1 minus 2x. This is x, and this is x. It's asking for the concentration of HI at equilibrium. Well, if you look on the graph on the previous page, at equilibrium, since HI is what's plotted on this graph, at equilibrium, HI is 0.08. So that means that this is equal to is it 0.08 or 0.8? 0.8, my bad. 0.80. Well, that allows us to find x immediately. That's the answer to this question. Okay, so this is 0.8 moles per liter. But let's go ahead and find x for the heck of it. And if you plug this all in and you solve for it, you get 0.2 equals 2x equals 0.2. Therefore, x equals, in this case, 0.10. And this one is 0.10. This is molarity. That's molarity. That's molarity. So pay attention to these numbers. We might have to go back and use those later. Determine the concentrations of H2 and I2. We just did that. At equilibrium, H2 is 0.1 and I2 is 0.1. Great job. So this is 0.10 and 0.10 moles per liter. I want to go back and remind you of how we got that one more time. If 1 minus 2x equals 0.8, okay, then negative 2x equals negative 0.20, x equals 0.10. Just making sure you know where I got that from. Okay. For D, so we did that, D. On the graph above, make a sketch that shows the concentrations of H2, we know it's 0.1, and O2 as a function of time. Well, let's find out where they were initially. Initially, it was 0, and finally, both were 0.1. So, if initial equals 0, and the equilibrium equals 0.1. Initially, they're both at 0, and there's 0.1. So that's what's going to happen there. And really, there is the equilibrium that's happening. I mean, that is clear as day. That's awesome. So this one went down, this one went up, total right shift. Alright, E says calculate the value of the following, Kc. Well, for Kc, all we're going to be doing is plugging in our equilibrium values into the Kc expression and going from there. So, for E, if this is 1, Kc equals H2 I2 over Hi squared, and that equals 0.1 times 0.1 over 0.80 squared, which equals 0.016. Really reactant heavy. Remember, there's no units on K. For 2, they're asking us for Kp. Well, we have our old equation, you get it from the equation sheet, that says that Kp equals Kc multiplied by RT to the change in N. And when we go through this problem, we know here that delta N equals 2 minus 2. That's moles of products minus moles of reactants. If you look at the balanced reaction, I can write that out for you. Well, you look at the balanced reaction, there's 2 moles of products and 2 moles of reactants. It's 0. So without even doing this problem, we're going to say that Kp is equal to Kc in this sense. And the reason being, if Kp equals Kc RT to the delta N, and that's 0, this whole thing is going to go to 1. And Kp equals Kc times 1. So Kp equals Kc, and Kp would be equal to Kc, which is 0.016. Alright. Going on to F. I didn't do F in class, but F is a pretty simple problem, so we're going to go ahead and do F. And I'll stop it if we run out of time here, but I'll try and do this as quick as I can. Basically, for this, it says that Kc is equal to 2.6 times 10 to the negative second. And it gives us this hypothetical experiment where 0.7 moles of Hi, 0.1 moles of H2, and 0.5 moles of I2 are placed in a container. Basically, all you have to do is go calculate Kc, and we're going to call this actually Q instead, because we're talking about initial values, not equilibrium values. We're going to pump that into the equation, and we're going to get 0.75, actually. We're going to get 0.50 multiplied by, and it's all in a 1 liter container, so the moles equal the molarity values, divided by 0.75 squared, and we're going to do that, and we're going to get 8.9 times 10 to the negative second. Now, 8.9 times 10 to the negative second, that is actually going to be greater, that is greater than your Kc of 2.6 times 10 to the negative second. So it asks you, in this case, determine whether the equilibrium concentration will be greater than, equal to, or less than the initial concentration. So in this case, this value is greater than the initial value for Kc. It asks you which direction it will. It actually doesn't tell you. This is going to shift left. And to establish equilibrium, Hi is going to have to increase. So it says, will Hi be greater than, less than, or equal to the initial concentrations? It's going to be greater than because it's going to shift left. Left, Hi is going to go up. And the other values are going to go down. I'm going to stop this one. Basically, this is just like problems 4, 5, and 6 in your topic 1. So go back and look at those. This is just like that. See you guys on 2004.